So I want to welcome everybody in for coming out to today's program with the Queen's Historical Society. My name is Jaron Halfpap. I'm the Education and Outreach Coordinator here at Kingsland Homestead, where I'm broadcasting to you today. I want to thank you guys for your interest in the history of computers for our program, It's Electric. This program was made possible by a contribution by Con Edison, and I'll talk a little bit more about what QHS does at the end of the program. Excuse me. I think it's just about time to get started. So let me get all this set up. Okay. So, for as long as there has been business, there has been a need to keep track of numbers and values to make sure that everything has been as squared away. In fact, that's why they think that writing was invented. Most cuneiform tablets that were found were to keep track of quantities and shipments and who was doing what. And so, for as long as that there has been math, people have been wanting to do more and more complex equations so they can solve more and more complicated problems. Because as we discover things in science, we try to apply mathematical models to them and see what we can learn. So the trouble with this is that humans are human. And so mistakes can happen. And when these mistakes happen in calculations, it can cause terrible catastrophes, including a satellite thinking that inches were actually centimeters, causing it to miscalculate its own speed, causing it to accelerate and crash into the asteroid that it was meant to investigate. It can cause things like leaving a couple of zeros off of a stock price and causing some computer to sell an entire inventory of stock for a fraction of what it was actually worth. So it's very important that when we're doing these calculations that we don't have mistakes. So nowadays we use machines to do all of these calculations because assuming that this machine is completely functional and is designed correctly and working as intended, it's not going to make mistakes. But before the days of electricity to power these computers, we used something else entirely: people. So I'm going to talk about the first computers. Obviously, these computers were people. Being a computer was actually considered a career for some people. Anybody who had an aptitude for math and was able to handle long, arduous series of calculations would be hired as computers to help break up the work of a mathematician or a scientist who didn't want to have to do the menial calculation work. This allowed scientists to just focus on the big picture stuff, and then they can send their calculations that need to be done and their equations off to another group to do it quickly, efficiently, and double check it. So one of the first examples, or one of the more well-known examples of early computers, was in 1757 when a mathematician, Alexis Claude Clairaut, when he wanted to tackle the challenge of when Halley's Comet was going to reappear. Edmund Halley had predicted that the comet would return, and by this time they had a mathematical model for how gravity works so that they could use to calculate its arrival. However, Alexis Claude Clairaut did not want to do that long and complex calculation because of all the different factors. So he broke the calculations up amongst a team, which included a fellow astronomer, Jerome Joseph Lalande, and Nicole Rien Lapote. You can see Nicole on the left here. Nicole Rien Lapote was a clockmaker's wife who enjoyed math. And she and Jerome Joseph Lalonde worked for 6 continuous months on this calculation. That should give you a good idea of how arduous these kind of calculations were and why Alexis Claude Clairaut did not want to do it himself. So Jerome and Nicole were able to calculate the arrival time of Halley's Comet correctly within 2 days, which at the time was an absolute achievement. Nicole Rien would continue her work as a computer, creating tables of pendulum oscillation rates, but the mathematician Clairaut, who had hired her, did not recognize Nicole Rien's contributions to his work. However, her partner, Jerome Joseph Lalonde, did work to ensure that she was acknowledged in future journal articles because he knew that she had done major contributions to that work. Computers would frequently be used in fields like astronomy, well up into the 20th century. Another famous example would be that of Wilhelmina Fleming, who you can see here in the center, and her work at Harvard. She and many other women worked to process photographic plates of the stars that had been taken by the male professors at the school, because the women were not allowed to really take part in the telescopic astronomy. Oh, I just noticed your comment on the volume. Unfortunately, everything's at maximum volume. I think it might be on your end that needs to be turned up. I'm seeing my audio levels are at near clipping. So the Harvard computers would process all of these photographic plates and catalog the sky. Wilhelmina's contributions actually helped create the system that we still use today for categorizing stars. Computers were also extensively hired during World War I and World War II, and especially during the Work Progress Administration era, to assist engineers. These positions of human computers were frequently opened up to groups that were otherwise blocked from what was considered prestigious scientific work. Very low for you too. Interesting. When I did an audio test earlier, I was having no trouble. Let me test it on my end as well. Okay, I do have the audio, but I can't make it any louder. Yeah, just double check. Very strange. All of my sliders are at maximum. The best I can do is turn it up over here, but then it might clip. All right, let's try this. So the human computers that were hired to assist engineers were otherwise blocked from prestigious scientific work. This was because the job was considered tedious, and many of the educated white male elite did not think that it was part of their position to do that kind of menial tasks. So they would typically hire women and people of color to do these kinds of tasks. But computers have not always been humans. We have been seeking to... Oh, is it only mono? Sometimes I have this problem. it's supposed to capture as mono speaker. I don't see the setting to fix that right now. I'm sorry. Let me try. No. Yeah, sorry about that. I'll have to go back and see if I can't fix that for the replay of the video. So we've been trying to supplement the human element of calculation with machines for many, many years. Specialized computers have existed in many different forms, including automata, which had been programmed to write messages, move around, sing, dance. They can be programmed, or even things like music boxes, which could be programmed to play music by using pins or holes to play music. But we've also had other aspects of ancient technology that helps us with our calculations. The Swanpan abacus, this is the Chinese style abacus, is very useful for holding calculations, so you don't have to memorize all of the numbers in your head. You can quickly manipulate the numbers on moving beads. The Antikythera mechanism, which was used to calculate tides, positions of stars, also act as a calendar. That was created in 770 to 200 BCE. And sundials are a form of computer. They calculate what time it is based off of the angle of the sun. And also, you can have hemispherical sundials to also account for the season. So all of these are ancient computers in their own right. But the idea of a mathematical computer is somewhat older than you might expect. So starting with Blaise Pascal's Pascaline, which was one of the first adding machines that could do a carryover, so it would automatically carry overflow from the ones to the tens to the hundreds to the thousands. That was constructed in 1642. We also have with the Leibniz wheel, invented by Leibniz. He was able to create a device that could also handle multiplication and division. So now we had devices that could do all four basic arithmetic functions by 1694. So these mathematical devices, Pascal and Leibniz, those would have been something created for royalty. They would have been something to hold in court, to impress visitors, to show, look at how smart the people of our area are. We're able to create these very fine machines that can do mathematical work for us. This is not something that would have been mass-produced or obtainable by even business people. However, by the 1800s, Charles Babbage started working on his machine. Babbage's machines are quite famous. However, probably the most notable thing about Charles Babbage's machines is that they were never built. They were entirely theoretical, but he had very meticulous plans drawn up, and he knew exactly how they would fit together, work, and he had everything documented, and he kept trying to find funders to fund the construction of this machine to prove that it could work. However, he was never able to do so. Mostly because Charles Babbage was a very strange fellow. Many people found it difficult to get along with him. A lot of people would say that Babbage's machines are actually the start of traditional computing, because his machines, such as the difference engine, which you can see here, was able to do polynomial math. You'll notice that it is completed in this picture because in the late 80s and early 90s, a museum in England actually funded the construction of this machine, and so they built it, and it does work. It was finished in 1991, and they do demonstrate it. It is a wonderful machine to watch. I highly recommend looking up a YouTube video of it. But Charles Babbage's second machine was the analytical engine. This machine would have been a programmable machine with methods of storing data and retrieving it. This would have been a humongous machine that data would actually travel down the line from module to module. So while neither machine was made in his lifetime, there were still people who were interested in it. One of those people was Ada Lovelace, and I'll get to her in just a sec. The local computer history museum has been working on a model of the difference engine. Wow, that sounds really interesting, Mark. Which computer history museum? So the analytical engine that Babbage had created would also have been important to create infallible tables, since other mathematical table books at the time were created by humans that sat there and made all of the calculations of every combination of variable, and they would put them in a book. This could lead to mistakes because humans were behind this. The idea behind these engines with their ability to make prints is that they would create an infallible table that would not have any mistakes in it. At this time, if someone wanted to look up, if someone wanted to quickly do math and they didn't know how to do a specific kind of equation, like a trigonomic function or a logarithmic function, they would purchase a book that would have all of the data in it so they could just look it up. But mistakes. So Ada Lovelace was one of those people who was interested in Charles Babbage's machine. Ada Lovelace was a mathematician. She loved doing math in her free time, and so she took an interest in Babbage's work after meeting him at a party. And so she continued to work closely with him, and eventually she actually created algorithms that would work for his machines should they be built later. You can see here in the middle, this is the diagram for computation by the engine of the Bernoulli numbers. So this is the equation that, or really the algorithm that would be Ada had designed to be put into the machine to calculate the Bernoulli numbers. So because of her work with these algorithms, many people credit Ada Lovelace as the first computer programmer, which is, I think, a really interesting title to have. But Babbage's machines were not the only mechanical computers. A lot of times, mechanical calculators could do complicated mathematics, such as harmonics, tide calculations, and other things. However, they're very specific. They're purpose-built. So on the left here, we have Lord Kelvin's tide calculator. By measuring tension on different wheels and pulleys, they could create an average to calculate tides, given their cyclical nature over time. This machine would have actually been one of the machines used to calculate tides for World War II, specifically during D-Day. Then you have Albert Michelson's harmonic analyzer. There's a wonderful YouTube series on how this machine works that I also highly recommend. I'll have links at the end of the video, at the end of this presentation. But this would be able to calculate the harmonic values in a given sine wave, even a complex sine wave. And it could also work in the reverse. Given a complex sine wave, you could calculate the harmonics. Then these mechanical machines did not stay as purely mechanical creations. In the 1880s, Herman Hollerith would create his electric tabulator. So this was a machine that he designed for the United States Census. In 1890, they had used this machine to help speed up the rate at which the census was calculated. And this was important because every decade, the census had been taking longer and longer, to the point where it was actually taking over 10 years, I believe, for the 1880 census to be completed. And so they introduced the electric tabulator for the 1890 census, and they actually managed to speed it up. And it still took many years to calculate, but it was still significantly faster and helped keep up with the expanding population of the United States. So this machine was actually electrical, and if you see this little lever that has what looks like a pin board to the left of it, that is literally a bed of pins facing down, and you would place a punch card on the table, and then you would use the lever to lower down the pins, and then the pins would drop through any holes in the punch card. And if there was a hole in the punch card, it would touch a vat of mercury that was inside the table, and then that would complete a circuit. And because the circuit was completed, it would turn a motor, and then those dials on the top of the machine would increase by 1, and so it would just count. It was a way of quickly counting. So the people who typically would operate these machines were frequently women. Women would be hired by the United States Census Bureau to tabulate all of the data that they had collected. And so they would punch the cards, verify the information, and then enter it in using this machine. So the IBM Tabulator, I should mention, Hollerith would go on to found, he would help to co-found the International Business Machines, or IBM. So some people consider it the first IBM machine. So the IBM Tabulator and the analytical engine both shared a feature in common, and that was the ability to input the data through the use of punch cards. This was a system of using paper and the holes, but it was not new to the computer world. So the punch card is actually a feature adopted from the Jacquard loom. This method had been used by looms throughout the late 18th century. However, it would be perfected by Joseph Marie Jacquard in 1804. By using these patterns of holes, they were able to input a system of instructions for the loom to follow to create complicated weaving patterns. This allowed them to make fancier designs with the explosion of the Industrial Revolution. And so they were able to keep up with the demand for new fashions of fabrics by using machines to weave these patterns instead of relying on a person to do so. These patterns could be looped. You can see the strings of cards with the holes in them. They're literally strung together, and then they can form loops so the patterns can repeat. So, with the advent of electric power, many of the first computers simply used the electricity to power relays and motors. These relays would use electromagnets to move plungers or other parts in and out of place depending on what was needed. Motors would turn gears without the need of a single person cranking like you would need to do for the Babbage analytical machine. you could get a electromechanical computer to do that for you. This would also be a transition that would be adopted into the desktop adding machines of even the late 60s, or even things like typewriters, where instead of relying on pure mechanisms, they make electromechanical machines to make it so that the user has an easier experience. But these electromechanical computers were huge, and a lot of the times this is where the concept of room-sized computers come from, because they would be made out of parts that were all hand-wired together. Someone would have to literally tie wires to pins, solder them, figure out where it goes, and manage thousands of wires at a time. I have a picture of a hand-wired central processing unit. It is an absolute mess of wires. I'll show that at the end. But here we have one of the first computers, Bomb. This was used during World War II by British cryptographers in Bletchley Park to help break the German Enigma code. This is what Alan Turing worked on. So this was a purpose-built computer. It was really meant only to do one function, break the Enigma code. But then only a couple years later, the Colossus Mark I was created, which was a general-purpose programmable computer. And the Colossus Mark II is just has additional features compared to that. And so the Colossus was also used to break cryptography. So they're very still narrowly focused computers. But yes, as you can see in here, a lot of these computers would be operated by women. We have the names of two of them on the side here, Dorothy Dubuisson and Elise Booker, working on the Colossus Mark II. Yes, Laura, there is a Katharine Hepburn movie about working on computers. I don't remember the name of it, but it was not uncommon for women to take these jobs at working with computers. And just like with the human computers being women, because the men scientists didn't feel like doing the calculations themselves, a lot of the times it was because the idea of inputting data into the computer was a menial task, and so they didn't want to be bothered with it themselves, so it would be relegated to women. So in 1944, the ENIAC was completed. This was the first general purpose digital computer, and when I say digital computer, I mean that it was used vacuum tubes and for transistors, so that way it was all electrically controlled rather than electromechanically controlled. Because of this lack of moving parts, it was significantly faster. This used up to 18,000 vacuum tubes, which were something that Thomas Edison would have helped pioneer. And so at this point, the computers are rapidly changing in their technologies, but because the ENIAC uses vacuum tubes, it needs to warm up before it can function, because vacuum tubes have to get hot before their function can be fulfilled. So that's where the warm up kind of comes from. You see that in TVs, amplifiers, anywhere you see a vacuum tube being used to control electricity, the warm up is where the tubes need to get hot. Thankfully, we don't have to worry about that as much these days. So in 1947, we started having solid-state transistors that did not use the vacuum tube. So now computers were able to really start to not only get faster, they're starting to get smaller. We have here is an example of a early transistor computer, the IBM 1620. Again, we have it being operated by women. They were very much present during all aspects of the creation of the computer. So these kind of computers would be considered second generation computers. This would have been from the 1950s to the 1960s. They still featured discrete parts, but they also had reel-to-reel tapes. So if you look in the background on the picture on the right, you can see those big reel-to-reel tapes. Those contained the magnetic tape inside, just like a cassette tape or a VHS. Those are where the data would be stored, because at this time, hard drives aren't a thing. And if you wanted memory, you had to hand wire memory, and you had to wire each bit, which meant if you wanted 1 kilobyte of memory, you'd have to wire 1,200 or 1,024 individual little things, which they did, and it sucked. So switching over to a magnetic tape system was far easier. These tape drives would spin back and forth because the memory would be stored in a linear fashion, as all Turing complete computers do. The memory is actually stored in a line. And if you look at hard drives today, they're actually still a linear thing, very much like the data on a CD-ROM or on a record from a vinyl record player. The data is just stored in a very tight spiral. It's just very, very small, but it is just a very tightly wound spiral of data. So, before I talk about Grace, I'm going to talk quickly about the third generation of computers, which is where integrated circuits were created. These were for creating, these paved the way for third generation computers from the late 60s and early 70s. Now, circuit board transistors and the functions of them could be put onto a single part rather than having to be hand built out of many parts. Now, computers could rapidly shrink in size because one part does many things. This also made it a lot more attractive to business consumers because now it can, the computer is something that isn't an entire room. So I absolutely have to talk about Grace Hopper if you're going to talk about the early days of computers. Grace Hopper was a rear admiral of the United States Navy who was a key figure in these early computers and making sure that they're programmable. So something to note about computers at this time were that they were made individually. So there wasn't just one way of making a computer. A computer would be designed by a team, built, and then typically it would reside at a large business, a government facility, or a university. Each one of those computers is slightly different. Each one of them has their own way of interpreting instructions. Each one of them is controlled in different ways. Each one of them outputs things in different ways. So every time you wanted to make a program, you'd have to make a program for that specific computer. But Grace Hopper was one of the people who helped popularize the idea that a machine-independent programming language, which meant that now with a common language across all computers, then code could be run on the computer in London and then the computer in Washington, D.C. You'd only have to write the program once. To do this, you need a compiler. The compiler, which Grace helped develop the compiler, which would turn the human typed code into machine readable bits and instructions. This is where COBOL comes from. COBOL is one of the first big programming languages. It stands for Common Business Oriented Language, COBOL, and it's still used today. The people who are able to write in COBOL are considered very valuable because they help maintain very old systems. One of the other fun things about Grace Hopper's contributions to programming is the computer bug. She famously found a moth and stuck it to the logs for the computer, and so we have a documented case of the first bug being found in code. Because the moth had died and gotten stuck inside of one of the mechanical relays of the computer, and it was preventing it from closing, and so the program wasn't working. So at this time, because the computers were so large, and one of the reasons why they were so large is so that way they could be opened up and people could go inside to fix the problems. And so Grace is commonly credited with creating that lingo of, oh, there's a bug in my program. Though there is something to be said that the idea of a bug in the program had already existed. She definitely popularized it. So with these, whoops, my slides are out of order. So with these large and expensive business computers, these typically would not be set up as one computer per person because of their size and expense. Typically, it would be one large computer that could be accessed by many people through terminals. Terminals were basically just a screen and a keyboard that would talk through usually telephone wires to the mainframe. And then the mainframe would do the calculations and then send back what you were doing to the terminal. Then people could share the computer at the same time, but usually it was one person at a time. I'll talk a little bit more about them later. So during this time in the 40s up to the 60s, specialized electronics were still being used. Most electronic tools would use analog signals and circuitry rather than just doing digital calculation. So we can have electronic analog computers on top of digital computers. One of the best examples of this kind of equipment is still being used today. It is the synthesizer. One of the Flushing, Queens natives, Robert Moog, was one of the first ones to create a commercially successful synthesizer. His circuits on his keyboards would be programmable, and the musicians could customize how the sound worked. These synthesizers were combinations of many different modules that would each process the signal in a different way, causing the signal to come out different each time. And so they had a mathematical basis and turned into art. One of these key figures who was critical in popularizing synthesizer music is Wendy Carlos, whose album Switched on Bach was wildly successful and became one of the best-selling classical albums of all time. Her work is also featured in Tron, as the soundtrack for Tron, Clockwork Orange, and The Shining. And Wendy Carlos is also a rather accomplished eclipse photographer. Yes, Robert Moog was from Queens. However, he did move to, I want to say it was Tennessee, where he spent the remainder of his life working with, I think, Fender. Another woman in computation history is Hedy Lamarr. You'll probably recognize that her picture is a glamour shot because Hedy Lamarr is quite a famous actress from the golden age of cinematography. or golden age of cinema. But Hetty, during the times that she was not acting, enjoyed inventing. And so she co-created an electrical mechanical system for frequency hopping in 1942. This invention used a piano roll, which was a sheet of paper rolled up that had punch cards or punches in it. And this would feed information to a radio communication system, and this would have changed which frequency it was using. So you could program a sequence of radio frequencies, and so only people who had the same piano rolls of frequency hopping information would be able to listen to what you were trying to do. It was a way of encrypting information. It also helped prevent people from jamming the signals, because now they didn't have an exact information of where those signals were. This invention was not built, it wasn't taken up by the military, where she did submit it for use, but the ideas behind it were still used, especially in Wi-Fi today and Bluetooth, where using frequency hopping allows us to fit more signals in a narrow space. That way our devices don't collide with each other. Here's our terminal computers. So like I mentioned before, terminal computers were usually just a screen and a keyboard. This is where the computer in the office would be. The computer itself would have been somewhere else in the building, but these are all very important computers to talk about, especially the Xerox Alto. This is one of the first computers to have a graphical user interface, which means that it had windows on it, so you could open and close programs like you do today. It also had a mouse. It was one of the first computers to have a mouse as part of its input, so that way users could click on things like icons. Before, computers would have been entirely controlled through keyboard. Over here we have a Nova system. In the bottom drawer that you see that's sticking out, that is a hard drive. That would probably be less than a megabyte worth of storage, but you can see just how chunky it is, and it would have also been very expensive. Then the IBM 2250, where there's a light pen. A lot of people don't realize that we have had the ability to use pens like a tablet on computers since well into the 70s. Oh, you know, I forgot to write down what year the Xerox Alto is from. I can get back to you on that at the end. I'll look back into my notes. The light pen actually works based off of how CRT monitors work. As the CRT is shooting the electrons into the screen, it happens one row at a time. So depending on where the pen is touching the screen, it'll change the offset at which it sees the light, and so it knows approximately where you are on the screen. And so it was kind of like an early mouse. So now comes the fourth wave of computers. This is the late 70s, early 80s. This is with the invention of the microprocessor. This is where we are able to make chips with many different parts on them all at once. And this allows computers to shrink even more, just like they did with the integrated circuit. The process for manufacturing silicon wafers, those large rainbow-colored discs, was perfected, and it allowed us to etch onto the surface all of the circuitry for our processors. So instead of making the transistor, we kind of carve the transistor out of the silicone, not silicon. Sorry. So, oops. There we go. This allowed us to make computers that were smaller and smaller and even cheaper. So now we have the Commodore 64, the PET, the Apple II, and the TRS-80. The PET, Apple II, and TRS-80 are considered the big three to start off the home computing phenomenon, really. With the release of those, it was basically just a race to see who could make the most powerful, the cheapest, and the fastest computers. So, one of the most famous examples of these computers that could fit on desks was the Altair 8800. This was essentially Microsoft's first computer. It did not have a screen. You inputted data with switches, but it did have a programming language, Microsoft Basic, which definitely helped cement Microsoft as the tech giant that it would grow up to be. Oh, yes, there it is in my notes, 1972. So, this is where we also start running into Moore's Law. So Moore's Law is this idea. Whoop, almost knocked over my glass of water. So Moore's Law is the idea that computers get more and more powerful at a near exponential rate. So you can see here that the transistor count, which is how many computations generally that a processor can do, that side of the graph is logarithmic. So while this line looks like it's a linear correlation, it's actually exponential. But you can see how starting in 1970 up until even today, the power of computers has nearly doubled every 2 years. Though a lot of people are saying we're about to hit a wall with Moore's Law, that we're not going to be able to make computers more powerful by just adding more transistors, because we're getting to the point where we're hitting the limits of physics with how small we're making our transistors, and it's getting harder and harder to make them smaller to fit more in the same space. So a lot of the technology for computers is about software and how to use the hardware that we have in more efficient ways. But I'm going to kind of race through modern computing and why modern computing is the way it is today. A lot of that has to do with the IBM PC. IBM created the PS2, which was very, very popular, and everybody started copying them. Because of the IBM, and by the way, we were still in the process of each computer is slightly different. So each computer has its own processor made by different companies, and they all have different instructions. But the IBM PC became so popular that people kept copying how its instructions were handled. The x86 architecture. That's what we use today, because it became so popular. Whenever anybody talks about, oh, I have a PC, it's because they're talking about an IBM PC. It's an IBM clone of an early IBM PC. It's just much more powerful. A lot of its popularity was due to DOS, which was a early operating system. And so in an effort to keep compatibility uniform across the board, we still use the IBM x86 architecture today. Apple, however, decided it wants to play its own game. And so Apple does not use the x86 architecture in the same way. And that's why we have these two different kinds of computers. They use similar processors these days. However, they've actually even created their own processor So now Apple has the M1 chip, which came out earlier this year. That's another example of now there's a new way of computers interpreting instructions, and so software isn't going to necessarily be compatible from one platform to the next. So that kind of wraps up what I have to say. I know that was a lot all at once, but I wanted to leave some time for any questions that you guys might have. And while you guys type up your questions, I'm going to load up some pictures of the old hand-wired parts that I was talking about. So, sorry, just gotta change my input. Oops. Oh no. Okay, so this is a memory module for the Cray supercomputer. You can see all of these wires would have had to have been hand done. That would have taken a very long time and would have been an absolute mess to keep track of everything. This is a picture of an early processor. You can see all of the pins that are sticking up to make it easier to tie the wires to. And there's also a memory module. You can see in here all of the little intersections. Each one of those is a little metal core that would hold either a 1 or a 0. So this is all of the memory on that computer. This would have been, I believe, 1 kilobyte. Another woman that I forgot to talk about, actually, is Margaret Hamilton. Margaret Hamilton is one of the NASA engineers who worked on the Apollo missions. She was one of the computers, the person computers who double-checked the code that helped take the Apollo rockets to the moon. So it was her verifying what the machine was doing. And you can see a stack of all of her code. It's almost as tall as she is. So women have been present in computers throughout history, and I think it's very important that we continue to recognize women in mathematics and science. So as we wrap up, I want to first thank you guys for coming out to today's program. And I wanted to also thank Kind of Edison for sponsoring this, for making this happen. But we also have more upcoming programs at Queens Historical Society. We have the Airfare program on April 10th. That is going to be talking about the history of airports and travel in Queens. I'm going to be talking about all 5 or 6 airports that Queens has had throughout the last century. It's quite fascinating. And then we also, if you're interested in computers and space exploration, we have our program From Queens to Mars, a Q&A session with the NASA scientist Vishnu Sridhar on April 3rd. That one's coming up soon. If you go to our website, you can actually click on the link for that program and submit questions that you want to ask Vishnu. And he's going to talk about what it was like to work on the Mars rover Perseverance that recently landed on the surface of Mars. Also, while you're on the website, please consider becoming a member. You can join us. You can find more information there. Your support for our programs would mean a lot to us. Oh, yes, a programmable carillon. Okay. by mentioning that it's a programmable cylinder, it sounds like it's a kind of like a drum for a music box that's has movable pins. Music boxes are easily one of the most classical forms of computers, in my opinion, because by all means they are programmable and they do a task. I also highly recommend the Spielclock Museum if you want to look at more old style mechanical things. I'm gonna see if I can't drop a couple of interesting links in chat. This is a things that I think you guys would be interested in watching as follow-ups once I've okay. This video is of a very large processor that's been exploded, in the sense that all of the parts are on the wall, and the LEDs show the data as it moves, and you can slow it down or speed it up. I think it's a wonderful example of how a processor actually works. And then there's also a the harmonic analyzer that I talked about earlier. That video is right here. So please enjoy. If you have any questions, feel free to email me if you didn't get a chance to ask them here. My email is jeranh, JERANH, at queenshistoricalsociety.org. So I hope everybody has a wonderful day, and thank you for coming.